Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. This is a podcast where I read old books, sometimes fiction, sometimes non-fiction, in the most boring way I can to try and help slow your spinning mind, enough for you to fall asleep in the most natural way possible. The stresses of life often follow us to bed and keep us company, but I'm here to distract you from them and help you to drift away. Before you do fall asleep, if you find Sleepy Time Tales helpful, and you'd like to support me to keep it going out to you and thousands of your fellow insomniacs, please consider supporting on the Patreon at patreon.com/sleepytimetales. If monthly is a bit much, you can also put a tip in the tip jar, and both of these things are linked in the show notes. You can also support Sleepy Time Tales by simply spreading the word. If you know someone is struggling to sleep, just tell them about it. And that's enough of that. We're getting back to learning about the sun and the inner planets of the solar system. So as we do that, snuggle down, close your eyes, breathe deeply, and listen closely as I lead you down the path to sleep. We return this week to Astronomy, the Science of the Heavenly Bodies by David P. Todd. Chapter 26. Sunspots and Prominences. Dark spots of a deep bluish black will often be seen on this photosphere of the sun. Sometimes single, though generally in groups, the larger ones will have a dark center called the umbra, surrounded by the very irregular penumbra, which is darker near its outer edge, and much brighter apparently on its inner edge where it joins the umbra. The penumbra often shows a species of thatchwork structure, and systematic sketches of sunspots by observers skilled in drawing are greatly to be desired, because photography has not yet reached the stage where it is possible to compete with visual observations in the matter of fine detail. The spots themselves nearly always appear like depressions in the photosphere, and on repeated occasions they have been seen as actual notches when on the edge of the sun. Many spots, however, are not depressions. Some appear to be actual elevations, with the umbra perhaps a central depression, like the crater in the general elevation of a volcano. Spots are sometimes of enormous size. The largest on record was seen in 1858. It was nearly 150,000 miles in breadth, and covered a considerable proportion of the whole visible hemisphere of the sun. A spot must be nearly 30,000 miles across in order to be seen with the naked eye. In their beginning, development, and end, each spot or group of spots appears to be a law unto itself. Sometimes in a few hours they will form, though generally it is a question of days and even weeks. Very soon after their formation is complete, tongue-like encroachments of the penumbra appear to force their way across the umbra, and this splitting up of the central spot usually goes on quite rapidly. Sunspots and violent disturbance are rarely observed. As the sun turns round on his axis, the spots will often be carried across the disk from the center to the edge, when they become very much foreshortened. The sun's period of rotation is 28 days, so that if a spot lasts more than 2 weeks without breaking up, it may reappear on the eastern limb of the sun after having disappeared at the western edge. 2 or 3 months is an average duration for a spot. The longest on record lasted through 18 months in 1840 to 1841. The position of the sun's axis is well known. Its equator being tilted about 7 degrees to the ecliptic, and the spots are distributed in zones north and south of the equator, extending as far as 30 degrees of solar latitude. In very high latitudes, spots are never seen. They are most abundant in about latitude 15 degrees both north and south, and rather more numerous in the northern than in the southern hemisphere of the sun. Recent research at Mount Wilson makes the sun a great magnet, and its magnetic axis is inclined at an angle of 6 degrees to the angle of rotation, around which it revolves in 32 days. There is a most interesting periodicity of the spots on the Sun. For months it will sometimes elapse with spots in abundance and visible every day, while at other periods, days and even weeks will elapse without a single spot being seen. There is a well-recognized period of 11 1/10 years, the reason underlying which is not, however, known. After passing through the minimum of spottedness, they begin to break out again first in latitudes of 25 degrees to 30 degrees, rather suddenly, and on both sides of the equator. As they move toward the equator, as their number and individual size decrease. The last observed epoch of maximum spot activity on the Sun was passed in 1917. Many attempts have been made to ascertain the cause of the periodicity of sunspots, but the real cause is not yet known. If the spots are eruptional in character, the forces held in check during seasons of few spots may well break out in period. The brighter streaks and mottlings known as faculae are probably elevations above the general photosphere, and seem to be crusts of luminous matter, often incandescent calcium, protruding from the lower levels. Generally, the faculae are numerous around the dark spots, and the absorption of the sun's light by his own atmosphere affords a darker background for them, with better visibility nearer the rim of the solar disk. The spectroheliograph reveals vast zones of faculae, otherwise invisible, related to the sunspot zones proper on both sides of the equator. In some intimate way, the magnetism of Sun and Earth is so related that outbreaks of solar spots are accompanied with disturbances of electrical and other instruments on the Earth. Also, the aurora borealis is seen with greater frequency during periods when many spots are visible. Within very recent years, the discovery of a magnetic field in sunspots has been made by Hale, with powerful instruments of his own design. Sunspots had never been investigated before with adequate instrumental means. He recognized the necessity of having a spectroscope that would record the widened lines of sunspot spectra, and the strengthened and weakened lines on a large scale. Certain changes in relative intensity were traced to a reduced temperature of the spot vapors by comparison with photographs of the spectrum of iron and other metallic vapors in the electric arc at different temperatures. Here the work of the laboratory was essential. Sunspots were thus found to be regions of reduced temperature in the solar atmosphere. Chemical unions were thus possible, and thousands of faint lines in spot spectra were measured and identified as band lines due to chemical compounds. Thus, the chemical changes at work in sunspot vapors were recognized. Then followed the highly significant investigation of solar vortices and magnetic fields. Improvements in photographic methods had revealed immense vortices surrounding sunspots in the higher part of the hydrogen atmosphere. And this led to the hypothesis that a sunspot is a solar storm, resembling a terrestrial tornado, and in which the hot vapors whirling at high velocity are cooled by expansion. This would account for the observed intensity changes of the spectrum lines and the presence of chemical compounds. The vortex hypothesis suggested an explanation of the widening of many spot lines and the doubling or trebling of some of them. As it is known that the electrons are emitted by hot bodies, they must be present in vast numbers in the Sun, and positive or negative electrons, if caught and whirled in a vortex, would produce a magnetic field. Seaman in 1896 had discovered that the lines in the spectrum of a luminous vapor in a magnetic field are widened, or even split into several components if the field is strong enough. Characteristic effects of polarization appear also. The new apparatus of the observatory, in conjunction with experiments in the laboratory, immediately provided evidence that proved the existence of magnetic fields in sunspots, and strengthened the view that the spots are caused by electric vortices. Extended investigations have led Hale to the conclusion that the Sun itself is a magnet, with its poles situated at or near the poles of rotation. In this respect, the Sun resembles the Earth, which has long been known to be a magnet. The Sun's axial rotation permits investigation of the magnetic phenomena of all parts of its surface, so that ultimately the exact position of the Sun's magnetic poles and the intensity of the field at different levels in the solar atmosphere will be ascertained. Schuster is of the opinion that not only the Sun and Earth, but every star, and perhaps every rotating body, becomes a magnet by virtue of its rotation. Hale is confident that the 100-inch reflector will permit the test for magnetism to be applied to a few of the stars. The Sun can be observed at Mount Wilson on at least 9/10 of all the days in the year, and the daily record of the polarities of all spots with the 150-foot tower telescope is a part of the routine. A method has been devised for classifying sunspots on the basis of their magnetic properties, and more than 1,000 spots have already been so classified. About 60% of all sunspots are found to be in binary groups, the single or multiple members of which are of opposite magnetic polarity. Unipolar spots are very seldom observed without some indication of the characteristics of bipolar groups. These are usually exhibited in the form of flocculi following the spot. The bipolar spot seems to be the dominant type, and the unipolar type a variant of it. Although devised for quite another purpose, that of photographing the hydrogen prominences on the limb of the Sun, the spectroheliograph has contributed very effectively to many departments of solar research. The prominences are dull, reddish cloudlets that were first seen during total eclipses of the Sun. Probably Vesenius, a Swedish astronomer during the total eclipse of 1733, made the earliest record of them, as pinkish clouds quite detached from the edge of the Moon. And in that day when it had not yet been proved that the Moon was without atmosphere, he naturally thought they belonged to the Moon, not the Sun. Undoubtedly, Loa, a Spanish admiral, also saw the prominences in observing the total eclipse of 1778, but they seem to have attracted little attention until 1842, when a very important total eclipse was central throughout Europe, and observed with great care by many of the eminent astronomers of all countries. So different did the prominences appear to different eyes, and so many were the theories as to what they were, that no general consensus of opinion was reached, and some thought them no part of either Sun or Moon, but a mere mirage or optical illusion. But at the return of this eclipse in 1860, photography was employed so as to demonstrate beyond a shadow of doubt the real existence and true solar character of the prominences. By the slow progress of the Moon across the Sun and the prominences on the edge, a unique series of photographs by De la Rue showed the Moon's edge, gradually cutting off the prominences piecemeal on one side of the Sun, and gradually uncovering them on the opposite side. The prominences then were known to be real phenomena of the Sun, some of them disconnectedly floating in his atmosphere as if clouds. Their forms did not vary rapidly. They were very abundant, and their light was so rich in rays of great photographic intensity that many were caught on the plate which the eye failed to see. They appeared at every part of the Sun's limb, and their height above it indicated that there must be many thousand miles in actual dimension. What they were, however, remained an entire mystery, and no one even thought it possible to find out what their chemical constitution might be, or to measure the speed with which they moved. A few years later came the Great Indian Eclipse, August 28th of 1868. At that date, the longest total eclipse ever observed. Janssen of France and many others went out to India to witness it. Fortunately, the prominences were very brilliant, and this led Janssen to believe it would be possible for him to see them the day after the eclipse was over. By modifying the adjustment of his apparatus suitably, and changing its relation to the sun's edge, he found that hydrogen is the main constituent in the light of the prominences. In addition to this, he was able to trace out the shapes of the prominences, and even measure their dimensions. His station in India was at Guntur, many weeks by post from home, so that his account of this important discovery reached the Paris Academy of Sciences for communication with another from the late Sir Norman Lockyer of England, announcing a like discovery, wholly independently. The principle is simply this, and admirably stated by Young. Under ordinary circumstances, the prominences are invisible, for the same reason as the stars in the daytime. They are hidden by the intense light reflected from the particles of our own atmosphere, near the sun's place in the sky. And if we could only sufficiently weaken this aerial illumination, without at the same time weakening their light, the end would be gained. And the spectroscope accomplishes this very thing. Since the air light is reflected sunshine, it of course presents the same spectrum as sunlight, a continuous band of color crossed by dark lines. Now this sort of spectrum is greatly weakened by the every increase of dispersive power, because the light is spread out into a longer ribbon and made to cover a more extended area. On the other hand, a spectrum of bright lines undergoes no such weakening by an increase in the dispersive power of the spectroscope. The bright lines are only more widely separated, not in the least diffused or shorn of their brightness. Simultaneous announcement of this great discovery by astronomers of different nations, working in widely separate regions of the Earth, led to the striking of a gold medal by the French government in honor of both astronomers and bearing their united effigies. Ever since the famous Indian eclipse of 1868, it has not been necessary to wait for a total eclipse in order to observe the solar prominences. But every observer provided with suitable apparatus has been able to observe them in full sunlight whenever desired, and the charting of them is part of the daily routine at several observatories in different parts of the world. So vast has been the accumulation of data about them that we know their numbers to fluctuate with the spots on the sun, and the distribution of a sun's surface resembles in a way that of the spots. While the spots and protuberances are most numerous around solar latitude 20 degrees both north and south, the prominences do not disappear above latitude 35 to 40 degrees, as the spots do. But from latitude 60 degrees they increase in number to about 75 degrees, and are occasionally observed even at the sun's poles. Faculae and prominences are more closely related than the sunspots and prominences. There are wide variations in both magnitude and type of the prominences. Heights above the sun's limb of a few thousand miles are very common, and they rarely reach elevations as great as 100,000 miles, though a very occasional one reaches even greater heights. Classification of the prominences divides them into two broad types, the quiescent and the eruptive. The former are for the most part hydrogen and the latter metallic. The quiescent prominences resemble closely the stratus and cirrus types of terrestrial clouds, and are frequently of enormous extent along the sun's edge. They are relatively long-lived, persisting sometimes for days without much change. The eruptive prominences are more brilliant, changing their form and brightness rapidly. Often they appear as brilliant sparks or jets, reaching altitudes that average about 25,000 miles. rarely seen near the sun's poles, are much more numerous near the sunspots. Speed of motion of their filaments sometimes exceeds 100 miles a second, and the changing variety of shapes of the eruptive prominences is most interesting. Oftentimes they change so rapidly that only photography can do them justice. Prominence photography began with Young a half-century ago, who obtained the first successful impression on a microscope slide with a sensitized film of collodion, as was necessary in the earlier wet plate process of photography, which required exposures so long that little progress was effected for about 20 years. Then it was taken up by Deland of Paris and Hale of Chicago, independently, both of whom succeeded in devising a complex type of apparatus known as the spectroheliograph, by which all the prominences surrounding the entire limb of the sun can be photographed at any time by light of a single wavelength, together with the disk of the sun on the same negative. The prominences appear to be intimately connected with a gaseous envelope surrounding the solar atmosphere, in which sodium and magnesium are present as well as hydrogen. The depth of the chromosphere is usually between 5,000 and 10,000 miles, and its existence was first made out during the total solar eclipses of 1605 and 1706, when it appeared as an irregular rose-tinted fringe, though not at the time recognized as belonging to the sun. The constitution of the sun and its envelopes is still under discussion, and no complete theory of the sun has yet been advanced, which commands the widest acceptance. Of the interior of the sun, we can only surmise that it is composed of gases which, because of intense heat and compression, are in a state unfamiliar on Earth and impossible to reproduce in our laboratories. Their consistency may be that of melted pitch or tar. Surrounding the main body of the sun are a series of layers, shells or atmospheres. Outside of all and very irregular in structure, indeed probably not a solar atmosphere at all, is the solar corona, parts of which behave much as if it were an atmosphere, but it appears to be bound up in some way with the sun's radiation. It has streamers that vary with the sunspot period, but its constitution and function are very imperfectly known, because it has never been seen or photographed, except at rare intervals on occasion of total eclipses of the sun. Beneath the corona we meet the projecting prominences, to which parts of the corona are certainly related, and beneath them the first true layer or atmosphere of the sun known as the chromosphere, its average depth being about 1/100th part of the sun's diameter. Beneath the chromosphere is the layer of the sun from which emanates the light by which we see it, called the photosphere. It appears to be composed of filaments due to the condensation of metallic vapors, and it is the outer extremities of these filaments which are seen as the granular structures everywhere covering the disk of the sun. The light shines through the chromosphere, and the spots or ruptures in this envelope. Between photosphere and chromosphere is a very thin envelope, probably not over 700 miles in thickness, called the reversing layer. It is this relatively thin shell that is responsible for the absorption which produces the dark lines in the spectrum of the sun. Under normal conditions, the filaments of the photosphere are radial, that is vertical in the sun, but whenever eruptions take place, as during the occurrence of spots, the adjacent filaments are violently swept out of their normal vertical lines, and these displaced columns then form what we view as the spot's penumbra. From the outer surface of the sun's chromosphere rise in eruptive columns vapors of hydrogen and the various metals of which the sun is composed. These and the spots would naturally occur in periods just as we see them. We have said that the sun is composed of a mass of highly heated or incandescent vapors or gases, whose compression on account of gravity must render the physical condition quite different from any gaseous forms known on the Earth, or which we can reproduce here. As the result of more than half a century of studious observation of the Sun and mapping of its spectrum in every part, and diligent comparison with the spectra of all known chemical elements on Earth, we find that the Sun contains no elements not already found here, but that a great preponderance of elements known to Earth are found in the Sun. The intensity of their spectral lines is one prominent indication of the presence of elements in the Sun, and the number of coincidences of spectral lines is another. Iron, nickel, calcium, manganese, sodium, cobalt, and carbon are among the elements most strongly identified. A few of the rarer terrestrial elements are of doubtful existence in the Sun, and a very few, as gold, bismuth, antimony, and sulfur, are not found there. And the existence of oxygen in the Sun is regarded by some experts as doubtful. But if the whole Earth were vaporized by heat, probably its spectrum would resemble that of the Sun very closely. What are the effects of the Sun, and sunspots in particular, on our weather? Is the influence of their periodicity potent or negligible? If we investigate conditions pertaining to terrestrial magnetism, as fluctuations of the magnetic needle and the frequency of aurorae, there is no occasion for doubt of the Sun's direct influence, although we are not able to say just how that influence becomes potent. If, however, we look into questions of temperature, barometric pressure, rainfall, cyclones, crops, and consequent financial conditions, we find fully as much evidence against solar influence as for it. The slight variations of the Sun's light and heat due to the presence or absence of sunspots can scarcely be sensible, and much longer periods of closer observation are necessary before such questions can be finally decided. The slighter such influences are, if they actually exist, and the more veiled they are by other influences more or less powerful, the more difficult it is to discover their effects with certainty. The importance of solar radiation in the prediction of terrestrial weather has long been recognized, but until very recently no practical application has been made. The Smithsonian Astrophysical Observatory at Washington, under the direction of Dr. Abbie, has for many years carried on at a number of stations a series of determinations of the constant of solar radiation by the spectrobolometric method originated by Langley. A new station in Calama, Chile has recently been inaugurated, at which the solar constant is worked out each day and telegraphed to the Argentine Weather Service, where it is employed in forecasting for the day. Abbot's new method of solar constant determination is based on the fact that atmospheric transparency varies oppositely to the variations of brightness of the sky. Increase of haziness presents more reflecting surface to scatter the solar rays indirectly to the Earth. Of course, it presents also additional surface to obstruct the direct rays from the Sun. By measuring the brightness of the sky near the Sun, it becomes possible to infer the coefficients of atmospheric transmission at all wavelengths. The direct observations and the complete deduction of the solar constant for the day can all be completed within 2 or 3 hours. Clayton of Buenos Aires has now employed these results in the Argentine weather predictions for 2 years, and the introduction of this new element in forecasting has brought about a pronounced gain in the value of the predictions. Its adoption by the weather bureaus of other nations will doubtless come in due time, and the new method take a firmly established rank in practical meteorology. Abbott's observations many years ago first called attention to the variability of the solar constant, through a range of several %, both from year to year, and in irregular short periods of weeks or even days. Abbott considers this the more likely explanation then that atmospheric changes should take place simultaneously all over the Earth. The Sun is but a star. The stars that are irregularly variable in light and heat are numerous, and the Sun itself appears to be one of these. Especially important to the agricultural and vineyard interests of Argentina is the question of precipitation, and Clayton finds this very dependent on solar radiation. At epochs of practically stationary solar intensity, there is little or no precipitation. But quite generally he finds that great decrease of solar radiation is followed in from 3 to 5 days by heavy precipitation. Direct temperature effects are also traced in Buenos Aires and other South American cities, lagging from 2 to 3 days behind the observed solar fluctuations. The station at Calama yields about 250 determinations of the solar constant each year, and the Mount Wilson station about half that number. They are the only stations of this character at present in existence, and others should be established in widely separated and cloudless regions, as Egypt, Southern California, and Australia. Uniformity in the methods of observing would be highly desirable, and the Smithsonian Institution has perfected the details of common control of such stations, which it is expected may be established at an early day. Chapter 27. The Inner Planets. Vulcan. About the middle of the last century, Leverrier, a great French astronomer, having added the planet Neptune beyond the outside confines of the solar system, sought evidence of a lesser planet traveling around the Sun within the orbit of Mercury. For many years, close watch was kept on the Sun in hope of discovering such a body in the act of passing across the disk, or in transit, as it is technically termed. Lescabeau, a French physician, announced that he had actually seen such a planet. Vulcan it was called, passing over the Sun in 1859. Total eclipses of the Sun would afford the best opportunity for seeing such a body, and on several such occasions astronomers thought they had found it. But the signal advantages of photography have been applied so often to this search, and always unsuccessfully, that the existence of Vulcan, or the intramercurian planet, is now regarded as mythical. Mercury. This planet is an elusive body that very few, even astronomers, have ever seen. It is not very bright, has a rapid motion, and never retreats far from the Sun, so that it was a puzzle to the ancients who saw it, sometimes, in the twilight after sunset, and again in the twilight of dawn. When following the Sun down in the west in March or April, Mercury is likely to be the best seen, twinkling rather violently and nearly as bright as a star of the first magnitude. Very little is to be seen on the minute disk of this planet, except that it goes through all the phases of the Moon: crescent, gibbous, full, gibbous, crescent. Whether Mercury turns round on its axis or not cannot be said to be known, because the markings that are suspected on its surface are too indefinite to permit exact observation. More than likely, the planet presents always the same side or face to the Sun, so that it turns around on its axis once, while traveling around the Sun in its orbit. Mercury's day and year would therefore be equal in length. Nor have we much evidence on the question of an atmosphere surrounding Mercury. Probably it is very thin, if indeed there is any at all. When Mercury comes directly between us and the Sun, crossing in transit, the edge of the planet as projected against the Sun is very sharply defined, and this would indicate an absence of atmosphere on Mercury. Transits of Mercury can occur in May and November only. There was one on November 7th, 1914, and there will be one on May 7th, 1924. The latter will be nearly 8 hours in length, which is almost the limit. Mercury's distance from the Sun averages 36 million miles. The diameter of the planet is 3,000 miles, and its orbital speed is 30 miles per second, the swiftest of all the planets. No moon of Mercury is known to exist, although many times diligently searched for, especially during transits of the planet. Venus. Brightest of all the planets and the most beautiful of all is Venus. Its path is next outside the orbit of Mercury, but within that of the Earth, so that it partakes of all the phases of the Moon. Like Mercury, it sometimes passes exactly between us and the Sun, a rare phenomenon which is known as a transit of Venus. Being without telescopes, the ancients knew nothing about these occurrences, but they were puzzled for centuries over the appearance of the planet in the west after sunset, when they called it Hesperus, and an early dawn in the east when they gave it the name Phosphorus. Venus is known to be girdled with an atmosphere denser than ours, and it seems to be always filled with dense clouds. It is the reflection of sunlight from its perpetually cloudy exterior which gives Venus her singular radiance. So brilliant is she that even full daylight is not strong enough to overpower her rays, and she may often be seen glistening in the clear blue daytime sky, if one knows pretty nearly in what direction to look for her. Venus is 67 million miles from the Sun, and as our own distance is 93 million miles, this planet can come within 26 million miles of the Earth. It is, therefore, at times our nearest known neighbor in space, excepting only the Moon and Eros, one of the erratic little planets that travel around the Sun between Mars and Jupiter. Also possibly a comet might come much nearer. Astronomers always take advantage of this nearness of Venus to us, if a transit across the Sun takes place, because it affords an excellent method of finding out what the distance of the Sun is from the Earth. A pair of these transits happen about once a century. There were transits in 1874 and 1882, and the next pair occur in 2004 and 2012. In actual size, Venus is almost as large a planet as our own, being 7,700 miles in diameter, as compared with 7,920 for the Earth. Her velocity in her orbit is 22 miles per second, and she travels all the way around the Sun in 7.5 months, or 225 days. Venus, from her striking brilliancy, always leads the novice to expect to see great things on applying the telescope. But aside from a brilliant disk, now a slender crescent, now half full like the Moon at quarter, and again gibbous as the Moon is between quarter and full, the telescope reveals but little. There is pretty good evidence that the markings thought to have been seen on the planet's surface are illusory, and so it is wholly uncertain in what direction the planet's axis lies. Also, there is great uncertainty about the length of the day on Venus, or the period of turning round on its axis. Probably it is the same in length as the planet's year. Once when Venus passed very close to the Sun, just barely escaping a transit, Lyman of Yale University caught sight of it by hiding the Sun behind a tall building or church spire. The dark side of Venus was turned towards us, and he could not, of course, see that. But the planet was clearly there, completely encircled by a narrow, delicate, luminous ring, which was due to sunlight shining through the atmosphere that surrounds the planet. Similar ring effects were seen by observers of the transits of Venus in 1874 and 1882, and from all their observations it is concluded that Venus has an atmosphere probably at least twice as dense and extensive as that which encircles the Earth. Spurious sets of lights of Venus are many, but no real moon is known to attend this planet. And after cataloguing the inner planets, that's the end of the chapter. I think I'm going to call it there. This book is really, really fascinating, being written so long ago. It's amazing how much was known and how much wasn't known. It's a really fascinating read. I'm loving this one. If you'd like to pick up where I'm leaving off, you can find the original on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night, and sweet dreams.